Hi everyone, welcome back. In this lesson, we're going to be talking about plate boundaries. We previously talked about plate tectonics, which is the idea that Earth is made up of a number of lithospheric plates, and those plates are moving around at all times, although very, very slowly. In this lesson, I want to talk about plate boundaries, and these are places where two plates meet, and they come in a few different types. We have divergent, convergent, and transform plate boundaries, and these all act a little bit differently. So we're going to talk about those three types, and we're also going to talk about the forces that are acting on those plates that are actually causing plate tectonics to occur and these plates to move around the surface of the Earth. So let's start our discussion by talking about those three plate boundary types. Like I said, Earth is made up of at least 20 or so lithospheric plates. Geologists actually don't all agree on how many plates there are, but you can assume that there are about 20 lithospheric plates, and that includes major plates like the Pacific Plate or the Indian-Australian Plate, as well as microplates like the Juan de Fuca Plate that exists here in the Pacific Northwest. Anywhere where two or more plates meet, we call that a plate boundary, and they come in a few different types. We have divergent plate boundaries, where plates are being pulled apart and new crust is being formed. We have convergent boundaries, where plates are being pushed together, and one of those ends up having to be subducted because there's nowhere else for it to go but down. And finally, we have transform plate boundaries, where we have two plates that are sliding side by side. So let's talk about each of these scenarios in detail. First, we have divergent plate boundaries, which again are where you have two plates that are diverging or moving away from one another relatively. These occur in ocean basins most often. I'll talk about how they get started in continents, but as they exist, they can be found at the bottom of the ocean. And this is where new ocean floor is being formed, new ocean crust is forming. And it takes place at what we call mid-ocean ridges. Mid-ocean ridges are relatively high elevations within our oceans, and you can see this mid-ocean ridge that exists down the Atlantic Ocean. And it's relatively high compared to nearby ocean crust because it's relatively buoyant and warm. It's new crust. It's just been formed. It's brand new. So it's relatively buoyant and tends to stand at a higher elevation than the nearby oceanic crust. And so the way that this works is you have these plates that are being pulled apart. For example, at one point, South America and Africa were together. Those continents were right next to each other, but they rifted apart and new crust is being formed in the center. Here's a sequence of what it would look like if you were to pull two continents apart. You have that mid-ocean ridge here where the ocean crust is relatively thin, and that asthenosphere is able to rise to the top, and that new crust is able to form. And as you continue to pull those plates apart, you get new crust forming in the centers. The oldest ocean floor ends up nearest to the continents, and the youngest seafloor is in the center. So if we were to zoom in on a mid-ocean ridge, this is sort of what you could expect to see. Again, this is at the bottom of the ocean, so you have to imagine that we've gone down in a submarine or something like that. So we have new crust that's being formed. It's usually basalt that is erupting at the bottom of the ocean. The asthenosphere, which has overall an ultramafic composition, what happens is it partially melts. As it rises, part of it is going to begin to melt, and that partial melting is going to cause it to change composition over time because not all of it is melting at once. So it goes from being ultramafic in composition to mafic in composition. And what ends up erupting at the bottom of the floor is basalt. And we get what we call basalt pillows very frequently because that basalt is actually erupting and it's cooling very quickly because it's hitting cold ocean water. If we were to look at a sequence of rocks from bottom to top of ocean floor, you would expect to see gabbro, where that asthenosphere has cooled and crystallized into a gabbro. It never erupted at the surface. You would expect to see sheeted dikes, so where magma actually was getting very close to the surface, it cools in these sheeted dike patterns. And then at the surface, when it actually erupts, you would see pillow basalts, and on top of those pillow basalts, you would see ocean floor sediments. So sediments that have settled on top of the basalt, including microorganisms and plankton, things like that are floating around in the ocean. One of the only places where you can actually touch two different tectonic plates at the same time is in Iceland. Iceland actually lies on the plate boundary between the North American plate and the Eurasian plate. And Iceland is essentially entirely ocean basalt. It just happens to be above the ocean elevation. But it is formed through these processes that we're talking about, through the rifting of two tectonic plates and the formation of new ocean crust. And like I said, you can go to Iceland and you can actually touch the two different tectonic plates at the same time. And there are actually places where you can go and snorkel or scuba dive between the two plates. Now, I want you to take a look at this map, and what this illustrates is the relative ages of the ocean floors around our planet. And in the areas where the seafloor is red, that's where it's relatively very young. And where the seafloor is these cooler colors, green and blue, that's where the seafloor is relatively old. There are a couple things that you might notice, including there isn't a whole lot of very old ocean floor, right? We see some blue and a little bit of purple here, but there really aren't ages that are much older than 200 million years. So we really don't have ocean crust that's any older than that. So I want you to start to think about why that is, why we don't have ocean crust that is much older than 200 million years old. The other thing I want you to look at is why we have some of these zones where the young red zone here is relatively narrow, and other zones here where that red young zone is really wide. So I want you to consider why we have wide swaths of young ocean crust and other areas where it's relatively narrow. If we go back in time and think about how ocean basins actually form, they often begin within a continent. So a continent that's experiencing what we call rifting, a continent that's being pulled apart. These are instances where the lithosphere is being stretched and thinned, and ultimately it becomes so thin that a basin forms and water fills in an ocean forms. Right now we have active continental rifting happening on our own continent in the Basin and Range province. Essentially, all of Nevada is being stretched apart. But if that process were to continue to happen, then ultimately Nevada and Southern California would be underwater. We also have continental rifting actively happening in East Africa. We call it the East African Rift. And one thing that's really interesting about continental rifts is because it's happening on our spherical planet, they actually require rifting in a 3-arm pattern. So in places like the East African Rift, you can see here that there are 3 arms to this rift. And what often happens is one of these rifts ends up failing, or it stops rifting after a while the rest of the rift continues. So let's talk about the next type of plate boundary, and that's convergent boundaries. And this is where you have two plates that are converging or coming together. Oftentimes this kind of becomes a competition between the two plates of which one's going to override the other. And that comes down to which plate is more or less dense. So the more dense plate ends up being subducted or forced underneath the less dense plate. Oftentimes, if it comes down to continental crust and oceanic crust, the oceanic crust is more dense, and so it's going to subduct beneath the continental crust, which is illustrated here in this figure. As this subduction happens, we say that the downgoing plate is being subducted, and the overriding plate is being abducted, or placed basically on top of that downgoing plate. As this process continues, we often get what we call flux melting, which is when you have very water-rich sediment being subducted down and heated up. And the addition of those volatiles, the water, causes the rock to melt at a temperature that is a lot lower than it normally would melt at. So we get what we call flux melting. And this causes a chain of volcanoes or a volcanic arc to form. So this is pretty typical of a subduction zone. You get a volcanic arc forming. At convergent boundaries, we also have a feature called an accretionary wedge or an accretionary prism. And this is essentially the accumulation of seafloor sediment that's getting scraped off the bottom of the ocean floor as it's being subducted. And this loose sediment, it's kind of like if you were to take a bulldozer and sort of like shove sediment into this wedge shape. That's basically what's happening to these seafloor sediments in these subduction zones. It's very common for earthquakes to occur at any plate boundary, but we get particularly violent earthquakes in these subduction zones. These can also form between two oceanic plates. The previous example I gave had a continental plate and an oceanic plate, but you can also get subduction between two oceanic plates, so long as one is more buoyant than the other. When you have two oceanic plates converging, you will often still get a volcanic arc, but they will be volcanic island arcs. They'll be appearing in the middle of the ocean rather than on a continent. If you were to continue this convergence or this pushing together of two tectonic plates, you would ultimately get a continental collision. You would have two continents that wind up converging and colliding with one another. It would form a mountain belt because now you have two very buoyant crusts that are competing. And so this is how we get mountain building. And we would call this a suture zone. So the suturing or sort of the collision between two different continents. The convergence of the Indian plate and the Eurasian plate is how the Himalayas were formed. And the Himalayas include the tallest peak on Earth, Mount Everest. And so that was quite a process. That involved the subduction of most of the Indian plate until the Indian land mass, the continent, ended up colliding with the Eurasian plate and forming the Himalayas. So this is exactly the kind of process that can form large mountain belts like the Himalayas. Another great example of convergence here on Earth is actually pretty much in our backyard. The Cascadia subduction zone is located in the Pacific Northwest, where the Juan de Fuca plate, that microplate I talked about, is subducting underneath the North American plate. This has a lot of implications for what it's like to live in the Pacific Northwest. It means that folks who live there experience many earthquakes, and they have the potential to experience quite violent earthquakes. So it's very seismically active. There's also active flux melting taking place, and there are active volcanoes in the region because of this. So some of those active volcanoes are probably familiar to you, including Mount St. Helens and Crater Lake, Mount Rainier. And these go even as far south into California as Mount Shasta and Mount Lassen. Those are also considered Cascade Range volcanoes, and they are active, and they are the result of active subduction. Let's talk about our final plate boundary type, and that is the transform plate boundary. And here we have two plates that are sliding side by side to one another, so we don't have any new crust being formed, and we don't have any old crust being subducted or destroyed. One place where we actually see a lot of transform plate boundaries is in the ocean, and this is one of the first places where they were actually identified. If you look at images of the seafloor, you can see that the pattern at those mid-ocean ridges is actually quite jagged. It's not just a straight line. And that's because these regions here, these dotted lines, are regions where the stretching is being accommodated by transform plate boundaries. And really what's happening here is you have different segments that are spreading at different rates. And so that's going to cause these transform faults to form in between the mid-ocean ridge segments. So one other area where you might know that a transform boundary exists is the San Andreas fault zone here in California. The San Andreas starts where the subduction between the Juan de Fuca plate and the North American plate ends at what we call the Mendocino Triple Junction. So this is a place where the three plates actually meet. So the Juan de Fuca plate, the North American plate, and the Pacific plate, they all meet at the Mendocino Triple Junction. The San Andreas fault zone runs through pretty much all of California, and it is what we call a right lateral transform fault. And we'll talk about faults in more detail in another lesson, but all you have to know is that the Pacific plate is moving relatively to the northwest, and the North American plate is moving relatively to the southeast. And so that causes a lot of earthquakes for those of us on the west coast. The San Andreas Fault Zone truly is a zone in a lot of places. That transform slip is accommodated by a number of faults, not just one discrete fault. But in other places, like here in this image on the right, you can see that there is actually a discrete fault trace. We are used to talking about fault lines and fault traces. Those are the lines where the fault plane actually intersects. But what you have to remember is that faults are planes. They are breaks between rocks that exist in 3 dimensions, and they're not just a line in the surface of the Earth. So some evidence of slip on the San Andreas Fault Zone is also kind of in our backyard. You don't have to travel very far to see this. If you go to Pinnacles National Park, which is one of our newest national parks in the United States, if you were to go and visit Pinnacles, you would be looking at an ancient Miocene age volcano. So the national park is basically made up of a lot of volcanic rocks. But what's interesting about it is Pinnacles is only one half of a volcano, and the other half of Pinnacles is actually down in Southern California, and it's called the Ninook volcano. It's about 195 miles south of Pinnacles. And the reason that this volcano had been split in half is because of the San Andreas Fault. So that just goes to show exactly how much slip has occurred on the San Andreas Fault, at least since the Miocene. I want to mention one thing about active versus passive margins. These are terms that you might come across. A continental margin is essentially where continent meets ocean, or continental crust meets ocean crust. That's what we call a continental margin. We say that these margins are either active or passive based on whether or not they are plate boundaries or not. So you can have a continental margin where you have continent meeting ocean, and it's passive because there is no tectonic action happening there. There is no plate boundary at that location. You can also have active margins where you actually have subduction or divergence or transform slip occurring. And that's what we would call an active margin. Now that we've gone over the different types of plate boundaries, I want to talk about the forces that are acting on these plates that are actually causing them to move around. One of the things that we thought was really key to plate tectonics, and now we know plays a little bit less of a role than we thought, is actually convection. So convection, again, is when you, let's say, take a pot of water, you're going to boil some water to make some pasta. What's happening is you have a heat source at the bottom that is heating up the water. The hot water rises to the top and the cold water sinks to the bottom, and you get what we call convection cells. This is what we thought was happening in the asthenosphere, and it is to an extent, but it doesn't really create these nice little neat convection cells that we used to think were existing in the asthenosphere. It's not. It's a little bit messier than that. So the top left here is sort of our old conception of convection in the asthenosphere, and sort of our new model is in the lower left here. So what you can see here in the lower left is that the warmer colors indicate warmer areas of upwelling, and the cooler colors indicate downwelling regions, or regions where earth materials are moving relatively downward. And again, we thought that convection was sort of the driving force of plate tectonics for a long time, but there's actually a lot of evidence to say that there are other influences on tectonic movement. One of those forces is actually what we call a ridge push force. And so this is occurring at divergent boundaries where we have two plates being pulled apart. And what's happening here is we have relatively buoyant, warm new ocean crust that's being formed, right? And it forms these ridges because it's relatively buoyant. So it creates these higher elevation regions, these ridges in the center of the ocean. And what that does is it actually puts a force on the nearby cooler lower elevation crust next to it. So these high regions are putting a force downward into the side on the neighboring crust. The illustrator here has sort of tried to show that this, if you were to put honey in a beaker, that honey naturally wants to flow away, down and away, because of the force of gravity. So that's sort of what's happening here at these mid-ocean ridges, is what we call ridge push force. So it's kind of pushing the crust away from the center. There's also what we call slab-pull force, which occurs at convergent margins, where you have one tectonic plate converging and subducting underneath another tectonic plate. And what's happening here is, as the plate begins to subduct, the more it subducts, the harder it's going to pull on the rest of the plate behind it. It's kind of like if you've ever ridden in a roller coaster and you're sort of rounding the hill at the top, right? That very first hill, you get to the top. And if you're sitting in the back of the roller coaster, you tend to feel more of a force pull you over the top of the hill because there is more roller coaster rounding the bend. So as more of the coaster begins to go down the hill, you feel more of that pull. That's kind of what's happening here in subduction zones. So as that plate begins to subduct, that force pulls a little bit harder on the rest of the plate. That's what we call slab pull force. That about wraps it up for plate boundaries. I talked about the 3 different plate boundary types: divergent, convergent, and transform. And I tried to give you some real life examples of where you might be able to find those different plate boundary types. And I also talked about the forces acting upon our tectonic plates and why plate tectonics is actually occurring. Thanks for joining me, and I'll see you in the next lesson.